Welcome to the Crazy Hat Chemist. So good morning, good afternoon, and good evening. So here we go. Today what we're going to be doing is we're going to be discussing nuclear chemistry for general chemistry students. So without further delay, let's get moving. Bam! So nuclear reactions. So what is a nuclear reaction and a little bit about it? So number one, nuclear reactions have an unstable nucleus, and that way it emits radiation or particles, those are emissions, and it is converted into a more stable nucleus or a different element, i.e. the atomic number and potentially the atomic mass is changed consequently. Okay, there is a very important law in science, and that's the conservation of mass. And this unit on nuclear reactions is also based on the conservation of mass, which we call the conservation of nucleons specifically. The nucleons are the protons and the neutrons. Those are the two subatomic particles which are inside the nucleus. So this is the first time that we're not discussing the electrons and the, quote, chemistry associated with an atom. The chemistry is associated with the electrons, and the nuclear reactions is associated with the nucleus. Of course, no way. Unbelievable. I know, it's amazing. All right, so there are three different common types of radioactive emissions. Now, there are more radioactive emissions than just these three, but these are the three most common ones. So if you want to go into further detail, then you should be watching my honors or AP chemistry videos. So let's get into the three most common types of radioactive decay. Number one is alpha decay. What is alpha decay? So the emission itself is a 4, 2, and an alpha. So you should see in that symbolic notation right there, there's a mass of 4, an atomic number of 2, and then there's the alpha symbol, that's a Greek letter. Okay, there's a generic equation associated with this, and we are using the standard nuclear notation. So if you look at the generic equation there, you should see AXZ. You are only starting off with one reactant, and you get two products. The one reactant is AXZ. That A is for the mass, the Z is for the atomic number, and the X is the symbol of the element. You should see that arrow. That arrow separates that one single reactant from the two products. One of the products is going to be an alpha particle that has a mass of 4, an atomic number of 2, and the alpha symbol. And then what happens is that there's a little bit of a math problem here, and that is, it's a simple math problem. We're going to subtract 4 from the original mass, and we're going to subtract 2 from the original atomic number. That will get me my new element, which is Y, and we're going to have to look that up on the periodic table. All right, our second type of radioactive decay that is most common is a beta particle. It has a mass of 0, that means it doesn't have a mass, but it has a charge of -1. This is effectively an electron. It has the beta symbol, which is a Greek letter again, and it is a scripted B with a tail on it. So you're going to start off on the reactant side with the AXZ, which is the element of your choice, and then it's going to decompose and it's going to disintegrate. It's going to release a beta particle on the product side, and the mass is not going to change. So the mass is going to remain constant, but yet the atomic number is going to increase by 1. So then you're going to have to look up and figure out what Y is based on an increase in atomic number by 1. Okay, now the third type of particle is a gamma particle. Gamma particles, you can see, is the Greek letter gamma, and it has a mass of 0 and a charge of 0. So this is effectively light, something from the electromagnetic spectrum. So we have that again, AXZ, that we're starting off with, and we get a 0, 0 that's released on the gamma, and then you have an A, X, and a Z. You notice that I have an asterisk on the product side of the new element, which it's actually not a new element. What is actually happening is with the release of that gamma particle, you're lowering the energy of that atom and the energy of the nucleus, and that becomes more stable over time. That's the deal, in short, in brief. All right. So let's keep on going and let's see what we're going to do here. What we're going to do is we're going to go into each of these three subparticles here. So the alpha decay, we're going to go into details about this one. So the alpha particle is actually a helium nuclei. So what I want you to do is go find yourself a periodic table, go find helium, it's atomic number 2, it has a mass of 4, an atomic number of 2, okay, and the electrons, the 2 electrons on helium has been removed and ripped off, and now you have a helium nuclei. That's why there's a 2+ positive charge, because there's 2 protons and no electrons in a helium nuclei. Okay, there's the mass of the particle, which is 6.65 times 10 to the negative 24 grams per particle. That has a very small mass. Okay, and what happens as an alpha particle is released from the nucleus is the decrease in mass of 4 and the atomic number by 2. Okay, what is an alpha particle stopped by? Well, an alpha particle is stopped by your thin dead layer of skin or a sheet of paper. So you could actually pull out a sheet of paper and stop an alpha particle itself. Okay, the range of an alpha particle in air is about 5 centimeters. That's only about that far. So you can either stop that particle with your hand, with your dead layer of skin, or you could pull out the lecture or a worksheet or just a piece of paper and stop an alpha particle with that. Okay, and furthermore, they do not travel very far in the air. The reason for that is relatively, in reference to the other 2 particles that we're going to discuss in just a moment, that's beta and gamma, the alpha particle has a very large mass. So you're going to have to imagine the alpha particle like I'm in a Ford pickup truck, an F-250 pickup truck, king cab, and I have it in neutral, and I'm going to say, hey, give me a push in the back of my truck and let me see how far and fast you push me. So with a certain amount of energy, of kinetic energy that you push that alpha particle, you push my F-250 truck, I'm not going to go very fast. Why? Because I'm very massive. So with a certain amount of kinetic energy, I'm not going to go very fast because I have a huge mass of 4, essentially. Okay, these have very high energy and they're relatively slow in velocity because they're so massive. Okay. This is what the alpha symbol is, and that is a 4-2, and it is like an alpha. That little alpha symbol is kind of like a fish swimming horizontally to the left. That would be one way to write it. Okay? All right, so there's that equation that we discussed on the previous slide. You start off with 1 reactant, and it's going to decompose into 2 products, and one of those products is the alpha. The mass is going to decrease by 4, the atomic number is going to decrease by 2. Okay, and then here is an example of an alpha particle emission. So I'm going to have uranium-238, and it's going to undergo alpha particle emission. You notice the arrow that I have here, it looks like an equal sign. So you're going to imagine the math as like an equal sign. So it's 238 is equal to 4 plus what number? Or 238 minus 4, that's equal to 234. That's the new mass of the new isotope on the product side. It's 234. Then I have an atomic number of 92 for uranium. That's 92 is equal to 2 plus what number? Or 90 minus 2 is equal to 90. So now I'm going to find 92 minus 2 is equal to 90. So now I'm going to look up 90 on my periodic table. That would be thorium, and that's why it's TH. All right, there's the alpha particle. It's very massive. It does not travel very far. Okay. The other way to write the alpha symbol here is to write the same numbers, 4 and 2, but an HE, because what is it? It's a helium nuclei. That's what it is. Okay, then we're going to talk about the beta particle. So the beta particle, what is it? It's a beta symbol. Okay, it's an electron, effectively. It has a charge of -1, just like an electron does. Okay, and it has a mass of 9.11 times 10 to the negative 28 grams per particle, and you should look up the mass of an electron that we've discussed before in atomic structure. It's the same mass. No way. Unbelievable, huh? So the atomic mass remains constant while the atomic number is increased by 1. Okay. What are beta particles stopped by? Beta particles are stopped by low density objects, so wood, plexiglass, and aluminum, about 1 centimeter thickness of aluminum. So they will go right through your hand, in other words. Okay, the range in air is about 12 meters. So that's a much longer distance. So you got to imagine that the beta particle here does not have very much mass in comparison to the alpha particle. So if I'm on a non-electric like razor scooter and I'm on that and you push me with the same kinetic energy, the same force that you pushed me with my F250 Ford pickup truck, then I'm going to go much farther, much faster on my scooter than I will on my pickup truck. And the reason is because the electron has much less mass. Hopefully that makes sense. Okay, the velocity is just slightly less than that of the speed of light. It's very low in energy relatively. And a beta particle, you might be thinking, wait a second, Mr. Montbriand, crazy hat chemist, dude, I thought we were talking about nuclear chemistry. And an electron is not in the nucleus. That's what you said at the very beginning of this little presentation. And that is correct. So what is actually happening? So since an electron is not in the nucleus, we got to figure out what's happening. And what is happening is the beta particle is ejected when a neutron decays into a proton and an electron. So let's go and figure out what that equation is. So what's happening is that a neutron from the nucleus, because this is nuclear chemistry, decays to a proton and an electron. It's that electron that forms, that is from that decay process of a neutron. That electron that's in the nucleus now is ejected out of the nucleus and ejected out of the atom. And that's what's actually happening. There's the beta symbol and the numbers associated with it. That's 0, -1, and a beta particle. And then here's that generic equation, just like what we had before. What's happening is the mass is not changing and the atomic number is increasing by 1. And here is an example. This is uranium-239, and it emits a beta particle. And you should see with this one here, the mass does not change. That's the top number, but the atomic number increases by 1. Okay, hopefully the math works out okay on that one for you. All right, let's move on to another one here, and boom! And the other way to write this is to write that beta symbol as an electron, and that works out fine too. Okay, cool. All right. The next one is going to be a gamma decay. And for the gamma decay, it's part of the electromagnetic spectrum. It's a photon, and I don't know if you've watched Star Trek or anything like that, but they have photon torpedoes. Those are just torpedoes of light. Okay, these are higher energy than X-rays. They travel at the speed of light. So you imagine how fast they're traveling. That is actually the speed limit of the universe, is the speed of light. Okay, it has no mass per particle and no charge per particle. Okay, so neither the mass nor the atomic number is changed in this process. There's no specific range. That means that these gamma particles travel great distances. So it's like me on an invisible carpet, and you're going to push me with the same kinetic energy that you push me in my F250 pickup truck, as well as on my scooter, and I am just going to go flying. Why? Because I have no mass, I have no charge. I'm going to go through just about anything. What are gamma particles stopped by? High density objects like lead. So thick lead, not just a little bit of thin little wafer lead, but thick lead. Okay, so after a beta particle is emitted, a gamma ray follows. That's what's happening here. Okay, the arrangement in the nucleus is unknown. There's the symbolic notation here of the gamma particle, and it's a 0 and a 0. The mass is 0, the atomic number is 0. And one way that students write this gamma symbol is to write like a fish. Instead of the fish traveling horizontally to the left, you can write that symbol like a fish diving deep into the ocean. So it's kind of like, you know, a fish is swimming horizontally, and then all of a sudden it sees a shark and like, oh my gosh, I'm gonna have to dive. So if you write that fish diving down, then you're going to be in good shape. Okay, And then here's that generic equation. Notice that I have that asterisk on that other product there. That lets me know that really the mass nor the number of the atomic mass or the atomic number has not changed. So that's important, and it's lower in energy. Okay, this is an example of something that undergoes a gamma particle emission, and that is iodine 125. Iodine 125 undergoes gamma particle emission, and what do you get? Iodine 125. No way. Okay, but that iodine 125 on the product side is lower in energy than the reactant iodine 125. That's the key part here. All right, let's keep on moving here. There's much more to cover. So we're going to talk about here the deflection of these three radioactive particles. So you should have an understanding. We got alpha, beta, and gamma. Alpha has a 2+ charge, beta has a -1 charge, and gamma has no charge at all. So you're going to take that into consideration as we look at this. So we're going to have this container here. It's going to be lead. We're going to have a radioactive source in it. We're going to have these slits for focusing, and these particles that are going to be emitted from this radioactive source are going to go right through this other side. It's kind of like having a container with a hole drilled through it, kind of like having a hydro flask, if you will, with the radioactive source inside of it. And you're going to point the radioactive source at something. Now it's going to pass, emitted particles are going to pass through a magnet. That magnet has a positive end and a negative end. So as it passes through that magnet, it's going to be deflected by that magnet if it has a charge. If it doesn't have a charge, it's not going to be deflected. We're going to figure out what is on the other side by using this photographic film or this luminescent screen, so we can detect those particles on the other side. That's our detection method. So our first particle is a beta particle, and beta particles are deflected by the magnet. Why are they deflected by the magnet? Because they have a negative charge. So they're going to be deflected by the negative end and attracted to the positive end of that magnet, if you will. Notice that that beta particle is deflected a lot. Why? Because its mass is very low. All right, then our next particle is the gamma emission. Now the gamma particle goes straight on through to the other side. It's not deflected by the magnet whatsoever. Why? Because the gamma particle has 0 charge to it. So that magnet does not deflect it whatsoever. Then we have the alpha particle. The alpha particle is deflected by the magnet because it has a +2 charge. But you see, it's the opposite charge of the beta particle, so it's deflected in the opposite direction. That is, it's deflected away from the positive plate, positive pole, and attracted to the negative pole of that magnet. Furthermore, you should see that that angle of deflection is less than the angle of deflection for the beta. The reason for this is that the alpha particle is more massive. So its deflection angle is going to be less because it's more massive. It's kind of like if you T-bone a big gigantic truck, then it's not going to be deflected as much as if you were to T-bone a really tiny car, and then it's going to move a large distance. That's the difference there. All right. Deflection of those radioactive particles, that re-emphasizes the fact that they do have charges and what those charges are. That is that scientific evidence-based information there. All right, now, these particles have penetration ability, and I've already discussed them individually, but I'm going to give you a graphic to represent that as well. So here we go. We're going to have a piece of paper. We're going to have some low-density objects like aluminum, wood, plexiglass, any low density objects. Then we're going to have relatively high density objects. That would be lead. Okay. Alpha particles, they're stopped by the paper or your dead layer of skin. Beta particles, they go right through the paper, but they're stopped by the low density objects. And gamma particles, they go right through the paper, right through the low density objects, and stopped by the high density objects of lead. And just to give you a reference, X-rays do the same thing as those gamma particles. So X-ray, gamma particle are very similar. They don't have any mass, they're traveling very fast. All right, that's that penetration ability of those 3 different particles, alpha, beta, gamma. All right, so now we're going to discuss some basic nuclear decay reactions here. We're going to do 3 of them here, and then you're going to go and look at my other video that has a worksheet with many examples. So this is just 2 of those basic examples. In order for you to do the worksheet problems, look at this, the next YouTube video, if you will, that discusses nuclear chemistry worksheet problems. And there are many examples. You need more practice. There's the examples right there. So we're going to write an equation for the loss of an alpha particle from the nucleotide platinum-194. So what you're going to do is you're going to find platinum on your periodic table. It has a mass that's close to 194. It is what? Well, it is PT for platinum, and it's atomic number 78. So I'm going to write that on my reactant side. And then it says it's going to undergo alpha particle emission. So I'm going to write the alpha symbol and the numbers associated with that. That's 4 and 2 and that alpha symbol. Then I'm going to do the math that's associated with this so that I can get the other product. Okay, so it's 194 in the numerator minus the 4. That should get my other numerator term. That's going to be 190. And then 78 minus 2, that's going to be 76. I'm going to look up 76 on my periodic table, and I'm going to find that element, and that will be osmium. So now I have osmium 190 as my other product. You should verify that your math works out correctly, and that would be 190 plus 4. Does that equal 194? Yes, it does. Additionally, 76 plus 2, does that equal 78? Yes, it does. Okay, perfect. Let's do another one. What nucleotide is formed when radium-228 loses a beta particle from its nucleus? So again, we need to look at our periodic table. We need to find radium-222 and then write down that isotope down. So that's 228, I apologize. So radium-228, I'm going to find that element on the periodic table. It's element 88, that's on Ra. I'm going to write the beta particle. So the beta particle is a 0 and a -1 with that beta symbol. Okay, so now it's 228 minus 0, so the new mass is going to be 228. 88 plus 1 on both sides with that -1, that's what our math tells us to do. So we're going to have 89. Now I'm going to look up 89 on my periodic table, and I'm going to find that element, and element 89 is actinium. It has a mass of 228. Perfect, done. Beta particle, check. Next one. What nucleotide will be formed when radon-222 emits a gamma ray? So, a gamma ray. What is a gamma ray? Here is, we're going to write down first radon-222. We need to find radon-222, that's element number 86. We're going to write down the gamma particle and what that is. And that's a 0, 0, and the gamma symbol, bam, there it is, right there. So this one is the easiest one to do, obviously. I'm going to look on my periodic table. Wait, no, it's right there. 222 minus 0, that's 222. 86 minus 0, well, that is 86. Piece of cake. So radon-222, it's element 86. You didn't even have to look at your periodic table to find that new element at all. You do know that that product of radon-222 is lower in energy because it has emitted a gamma ray. So consequently. All right, let's talk about the next one. It's a radioactive decay series. This is a decay series. It starts off with, what is that, uranium-238, and it decays via a process. When elements decay, they, especially when they go through alpha or beta decay, not gamma decay, but if it goes through alpha or beta decay, then what happens is it changes the element because the atomic number changes, and that's called transmutation. When one element changes into another element, this is through alpha or beta decay, that's called transmutation. Okay, and so this uranium-238 is going to transmutate into lead-206 over a period of time. Okay, and again, what I really need you to do is I need you to watch my other video, which gives many examples of single decay processes, and one of them gets you all the way down to lead-206. And lead-206 is a stable isotope. That's the important point here, is that lead-206 is stable, and then we end with lead-206, which is a stable isotope. All right, fantastic. All right, a simple question, why are some elements radioactive? Here's the short answer. The short answer is, well, they're unstable. Then the question is, what makes them unstable? Well, there are too many protons, or the ratio of protons to neutrons is not optimal and creates this instability in the nucleus. So for low mass atoms, that's atoms less than 20 or up to 20, stable isotopes have a 1-to-1 ratio of protons to neutrons. So neutrons, that's N, protons, Z, that's the atomic number. So the 1-to-1 ratio for the first 20 or so elements, those are stable. After you get beyond element number 20, in order to have a stable nucleus, what you need to do is add in more neutrons. Those neutrons create this binding force that is necessary for the nucleus to become more stable. That's an important concept there, okay? All right, so this graphic here shows a lot of information here. It's a vertical line that's on the y-axis of neutrons. Horizontal line, that's the x-axis for Z, which is the atomic number. So vertical line, number of neutrons. Horizontal line, number of protons, atomic number. Okay, so on this graphic, you should see that there's a very black thin line. That's where the atomic number and the neutrons are equal. In fact, there's this area of stability, which we call the band of stability of the nucleus. Okay, and that is on my graphic here. You should see that staircase black line. Look carefully at that staircase black line. That is 1-to-1 with the neutrons and protons initially, and then it starts deviating from that and curving up. That's why you need more neutrons in the nucleus to create that binding energy for more stability. Okay, based on this graphic of all the elements and all the different isotopes that there are, we can actually give some idea as to what kind of nuclear decay will occur. So if you are below that band of stability, then you have too few neutrons. And what you're going to do is going to go through electron capture or positron emission. These are two different types of radioactive decay that we are not discussing in this general chemistry course, which we do in the honors chemistry course. So you might want to look at that. If you are above this staircase line, then you have too many neutrons and you're going to go through beta emission. That will decrease that number. Now, if you're in the upper section there, you should see that that black staircase line just kind of disappears over time, and that means you have too much mass and you're going to undergo alpha particle emission. So this really gives you an idea of, based on this proton to neutron ratio, where you are on that band of stability and what kind of particle emission. So you can make some really good predictions as to what kind of particle emission, because it's scientific, folks. That's right. All right, here is a graphic of radioactive decay. Okay, so on the y-axis is a percent remaining, starting at 100% at the top, okay, going all the way down to 0. On the x-axis is the age of the sample in just random, like not random, but sequential ages of 1 through 8, so years, okay? And so we're going to start off with 100% of our sample. That's what we have originally. And then we're in a half-life. We're going to have 50% of that sample remaining. Then, in another half-life, 25% of the original, or half of the previous sample. And we're just going to keep on going, another half, and we keep on dividing these by 2. Let me give you an example with a piece of paper. Let me get that here. Don't go away, I'm coming right back. All right, so here is a full sheet of paper. So this would be 100% of my sample. In a half-life, then what's going to happen, that paper is going to cut in half. And so this half of the paper has decayed to a different element, maybe via alpha or beta. How much do I have left? I have half, 50%. In another half-life, then half of that decays into another isotope, and now I have 25% of my original sample. In another half-life, then I'm going to have 12.5%. In another half-life, I'm going to have 6.25%. etc. And then this is just going to keep on slicing in half, if you will, over time. How long does it take a half-life? Well, you're going to have to look at my honors chemistry videos for that. Okay, but sometimes half-lives are in time frames of milliseconds to minutes to hours to days to weeks to years to millennia to billions of years. Okay, and when do we really care? Well, when that radioactive sample is so small that it's background radiation, and then we ignore it. All right? All right, here's a half-life calculation for you. It says, how much will remain of a 32-gram sample of uranium-238 after 9 half-lives? So what we're going to do is we're going to do like a little T-chart. That T-chart is a little table. We're going to have the amount and the number of half-lives. So we're going to start off with our 32 grams at 0 half-lives. That's time frame 0. So in 1 half-life, I'm going to take that 32 and I'm going to divide it by 2. And then I get 16. So in 1 half-life, how much of the original sample is left? 16 grams. I want to get how much is left after 9 half-lives. So I'm going to take that 16, divide by 2, and I'm going to get 2 half-lives. I'm going to take that 8, divide by 2, and get 3 half-lives. I'm going to take that 4, divide by 2, and get 4 half-lives and 2 grams. I'm going to take that 2, divide by 2, and I'm going to get 5 half-lives, so that's 1 gram. I'm going to keep on doing this. So I'm going to keep on the amount I'm dividing by 2, the number of half-lives I'm just adding 1 each and every time. At 6 half-lives, I have a half a gram. At 7 half-lives, I have a quarter of a gram, or 0.25 grams. At 8 half-lives, I have 0.125 grams. And oh my gosh, it looks like I'm getting 8 half-lives here. And sorry about the 9 half-lives. So, wrong problem. So we're going to 8 half-lives and not 9 half-lives. Apologize for that. Okay, we're going to get what percentage remains after 8 half-lives. So we're starting off with 100%. We're going to divide that by 2. That's 50%, 25%, 12.5%. Divide by 2 again, 6.25, 3.125. Keep on dividing by 2 until you get to that 8 half-lives. And I apologize, that should be 8 half-lives, not 9 half-lives. All right, looking good there so far, with that correction right there for the 8 half-lives instead of the 9. All right, let's keep on going. That's a simple example of half-life problem. All you have to do is keep on dividing by 2. It's really simple. We're going to do a little summary of a comparison of fission and fusion. Okay. All right, so fission. What is fission? Here's a reaction of fission, and this is the reaction that occurs in most nuclear reactors here, and this is uranium-235. You take a neutron, you add a neutron to uranium-235, and you get a fission reaction, which is actually splitting. You're going to take a very heavy, dense isotope, and you're going to split it. And you're going to get barium and krypton in this particular case, and then you get 3 neutrons. What's really important is that you get 3 neutrons. So you add in 1 neutron and then you get 3 neutrons. This will lead to this exponential growth, or a chain reaction. There's a whole bunch of energy in terms of heat that's emitted out of this reaction, so that's really important. Okay. You should see that the word fission has 2 S's in it, so I can actually split the word into 2 right between the 2 S's, and that's what fission is. It's splitting. Fusion, on the other hand, here's an example of what can occur inside the sun, and that is hydrogen 2 and hydrogen 3. That's deuterium and tritium. You combine these 2, that's a fusion. It's kind of like gluing. What do you get? Helium and a neutron and energy, and a whole bunch of energy, more energy and heat than you do in the fission reaction. In fact, there's 4 times the amount of energy generated from a fusion reaction as opposed to the fission reaction, considering the same mass and type of fuel. Therefore, fusion is more efficient, and it's much cleaner than a fission reaction. So if you want to have a nuclear power plant someday, then you need a fusion reaction. However, we don't have any fusion reactions that we know of that we can control here on our planet. That's a sad thing. Okay, they're all bombs. All right, so nuclear fission reactions. Okay, you see that I've divided these S's in half right there. I can divide the fission and split the fission. So that's what fission reactions are. They're actually a heavy nucleotide splits into two or more fission products or fragments that are lighter than the original. Okay, it's a decomposition reaction, if you will. Large quantities of energy and heat are produced in a fission reaction. Okay, this leads to chain reactions and an exponential reaction rate growth. That's why those 3 neutrons were very important. Nuclear power is generated this way on our planet and our Earth that we do as humans. The atomic bomb is an example of a fission reaction. Okay, this is a nuclear aircraft carrier. It runs via this fission process. This is a nuclear submarine that runs via this process. These are nuclear reactors. They run via this same process. And that's an atomic bomb, and that's an uncontrolled reaction, right? In the nuclear aircraft carrier, the nuclear submarine, and the nuclear power plant, those are all controlled reactions. To slow this down, what you need to do is put absorbing compound, neutron absorbers in between the uranium-238. This is what's happening inside of a nuclear fission reactor. So on the left-hand side, you see this like dome that you see. This is the core of the reaction process here. And you have your uranium rods in there. And then you also have some other rods like boron and carbon that absorb neutrons. So as you pull out the neutron absorbing rods, then neutrons interact with the uranium that is there. That will heat up the water that is surrounding this. That water turns to steam. That steam turns turbines, which generates electricity. You just need to keep on recycling water through this whole entire process. What's generated? Heat. That heat turns the water into steam, which turns the turbines and generates electricity. Nuclear reactors are really the way to go. They're a fantastic source. We have an immense amount of nuclear fuel ready to be used. And well, the problem is there a meltdown? Potentially, but I think that the risks highly weigh out that. In fact, we could come up with a breeder reactor, and breeder reactors don't melt down. Those are a different kind of reactor than all the reactors that we have, except experimental breeder reactors. That's a really good type of reactor. We should be using something like that for generating electricity. If your country wants to be free from other countries, from fossil fuels and all those other things that are huge carbon sources, then get nuclear reactors. Are they expensive to build and maintain? Yes, but they generate an immense amount of energy and last a very, very long time. Then there are fusion reactions. So a fusion reaction is kind of a gluing of things, and this process is of uniting 2 nuclei together. This happens at very high temperatures and pressures to surpass that repulsive force of having the nuclei close together, because they actually need to fuse. Okay, so immense, huge quantities of energy are generated with this one, much more larger than the fission reactions. What does this? The sun. What else does this? The hydrogen bomb. That's again an uncontrolled reaction. Okay, there is no controlled fusion on Earth at this moment in time as of the recording of this video, but maybe you are the one to come up with a controlled fusion process. If you are, I guarantee you will get a Nobel Prize, a little bit of money from that Nobel Prize, about $1 million or so, and you'll generate some patents if somebody doesn't own all that information, and you'll make tons of money because everyone will want a fusion reactor to power their cities. This is much cleaner than fission by far, because what's generated is heat and non-radioactive isotopes for the most part, like helium. And heck, you could just make a bunch of party balloons and celebrate your fusion process. There's the sun, that's under immense amount of heat and pressure. That's why this occurs in the inner portions of the sun. Okay, and this is a hydrogen bomb. That's not a good thing. That's an uncontrolled reaction. Both of these are.